So this portion is continuation for the 1H NMR of inorganic complexes. So now we will see the fluxional inorganic complexes. So what is a fluxional? Fluxional means any molecule will be having more than one conformation. More than one conformation. So the energy also will be same. So those molecules we will call as a fluxional molecules. They shows different kinds of conformations. And now we will see some of the inorganic complexes, how they differ in their NMR spectra at different temperatures. So we have here ruthenium N4 C8 H8 CO3. So now we want to see the NMR spectra for this complex. So here the hapticity of this C8 H8 is 4. That means some ruthenium is binding to 2 double bonds. So ruthenium is here, this is binding to this double bond, CO, CO, CO. And in this conformation, in this form, it's very difficult to identify how many protons here we will get, how many different types of protons. So it's better to write in another conformation that we can write this one like this also. And here we have ruthenium. So now here we can see these two belongs to one set, B, C, D. So here we have to get 4 signals. So here for this proton we'll get a doublet, here triplet, and this is also triplet, and this is doublet. So we're supposed to get 3-line signal, 2-line signal, another one more 2-line, 3-line signal. Okay, so now but this NMR we get at minus 145 degrees centigrade, minus 145 degrees centigrade. And if we increase the temperature to minus 114 degrees centigrade, so here we will get like this spectra. And further, if we increase the temperature to minus 98 degrees centigrade, so here we will get a 2 broad lines. And further, if we increase temperature to minus 84 degrees centigrade, so here we will get a broad line. So the fluxional behavior here, it's changing. See, whenever we have a temperature, more temperature here, see, the rate of exchange should be equals to the NMR time scale. Rate of exchange should be equals to NMR time scale. So then only we will get different signals for different types of conformations. So here at 84 degrees centigrade, the rate of exchange was very fast. So because of that, we get a broad singlet. At minus 98 degrees centigrade, it was a little bit slow. So we got a 2-line signal. And at minus 114 degrees centigrade, we got 4-line signal. At minus 145 degrees centigrade, we got this kind of spectra. So at minus 145 degrees centigrade, it is very easy to predict the NMR spectra. So here we got 2 triplets and 2 doublets. So it's supposed to be, we're supposed to get like this spectra only. So we are getting it as at minus 145 degrees centigrade. And at this temperature, rate of exchange is equal to the NMR time scale. So like this we can explain by taking temperature for this molecule. And this question they have asked in a previous CSR exam, I think. And we have another example here. We have N1 C5 H5 twice, and N5, C5, H5 twice, and titanium. So here we can write this complex like this. So these two are N1 and these two are N5. So if we record the temperature at 62 degrees centigrade, we will get a broad singlet. At 36 degrees centigrade, we will get a still broad singlet, and 26 degrees centigrade we will get a two-line signal, and at minus 27 degrees centigrade we will get a two sharp signals. So here we have two different types of cyclopentadienal. It's here N5 and here is N1. So here with respect at high temperature there is an exchange from the N5 to N1 as well as N1 to N5. So because of that, this exchange is very faster than the NMR time scale. So because of that reason, NMR cannot identify how many different protons are there. Instead of identifying different protons, it just gives average. So it will shows all are equivalent. So because of that reason, we got a broad singlet at 62. Whereas at minus 27 degrees centigrade, we got a sharp signal, because the rate of exchange for N5 and N1 here is very slow. So because of that reason, we got a sharp signal. And further, we cannot expect that three different sets here, because here I already told the wedging concept in my previous video. So this, in case of cyclopentadienal, we will come across the wedging phenomena. So in wedging phenomena, it because of means around the axis there is a rotation. So because of that, all the protons will be same in a cyclopentadienal. So at minus 27 degrees centigrade, we get two sharp signals. That is for the one is for N5 cyclopentadienal, another one is for the N1 cyclopentadienal. And similarly, we have this so here we have cyclopentadiene, which is attached to the metal. So here we have three different sets of proton, Ha, Hb, and Hc. Okay, so at minus 32 degrees centigrade, it gives a broad singlet, because the wedging will be there. As we reduce the temperature from minus 32 to minus 67 degrees centigrade, the wedging will be slower. So here at this temperature, rate of exchange will be equals to the NMR time scale. So because of that reason, we will get a three-line signal here. Okay, so at minus 32 degrees centigrade, we will not getting a three-line signal. We are getting average signal. There is only one signal because the wedging phenomena. But at minus 67 degrees centigrade, we got the three peaks, because here the rate of exchange wedging, we can say wedging is slower, or rate of exchange also we can explain this one. I think for cyclopentadienal, we have to focus on wedging only, not rate of exchange. And here too we can explain by the rate of exchange, because N5 is changing to N1 as well as N1 is changing to N5. And another example, we have Al2 CH3 6 times. So this is the structure, looks like just like diborane. Here one CH3, another CH3, CH3, CH3. Next, if you see at high temperature, we will get a single line at high temperature, and at low temperature we will get a two lines. Okay, so because here we have a terminal methyl groups as well as bridge methyl groups, so there will be exchange between the terminal to bridge and bridge to terminal. Because of that, at a high temperature we will get only one line, whereas at low temperature this exchange will be slower. So because of that reason we get a two peak for the this complex. And one last example we have here, that is Fe2 C5H5 twice CO4. So this exists in two form, cis form as well as trans form. So cis form looks like this, Fe, this is Cp CO, Cp CO, this is trans form. So this is in equilibrium with cis form. Cp. So there is an equilibrium between the cis form as well as trans form here. There is an equilibrium between cis form as well as trans form. So if we record the NMR spectra for this complex at minus 28 degrees centigrade, sorry, plus 28 degrees centigrade. If we record the NMR for this complex at minus plus 28 degrees centigrade, we will get a singlet here. Okay, and where we will go for minus 70 degrees centigrade, here we will get a doublet. So because here in this case this complex is existing in the form of cis as well as trans. Okay, at at 28 degrees centigrade at high temperature we cannot differentiate trans and cis. They both are equilibrium, so they will show only one peak. As we lowering the temperature, so they are showing two different peaks. Okay, this is for one Cp, maybe trans, or this will be cis. This will be trans Cp as well as this will be cis cyclopentadienyl group. So this is about the fluxional behavior for inorganic complexes. I hope everything is clear. Thank you.